In this video, we're going to have a look at calculations involving complex numbers. So a reminder, a complex number, we can, given the letter Z, most of the time is in the form of A plus BI. A is the real part and B is the imaginary part of our complex number. So when we're dealing with complex numbers, for them to have any value, they must obey our understanding of our basic arithmetic rules. So for our calculations, let's assume that Z is -2 subtract 5i and W is the complex number 4 subtract 3i. So to add and subtract complex numbers, just like a coordinate or in a vector in component form, we're going to add complex numbers exactly the same way, real parts together, imaginary parts together. So in evaluating W subtract Z, we're simply going to say 4 subtract 3i subtract -2 subtract 5i. So our real parts are going to go together, so 4 subtract -2, that's going to give us 6, and -3i subtract -5i will be -3i plus 5i, and that will give us +2i. So W subtract Z is the complex number 6 plus 2i. Multiplication, well, when we're just multiplying by a scalar, we just simply expand that bracket into our complex number. So we've got two lots of 4 subtract 3i for W plus Z. So this is going to give us 8 subtract 2, which is 6, and -6 subtract 5 will be -11i. So 6 subtract 11i. When we're multiplying a complex number by another complex number, we're going to treat this as a binomial expansion. So when we're evaluating WZ, we're going to have 4 subtract 3i multiplied by -2 subtract 5i. So using our binomial expansion skills, we've got 4 times -2 is -8, 4 times -5i is -20i, -3i times -2 is +6i, and -3i times -5i is +15i squared. Now in simplifying this, we've got -8 subtract 14i plus 15 lots of -1, because we know I squared is the same as -1. So in simplifying this, we end up with -8 take 15, which is -23, subtract 14i. Let's have a look at division. When we've got a complex number divided by a real number, then that's quite simple. It's like multiplying by a scalar of a half or a third, for example. But a complex number divided by a complex number means we've got a situation such as W divided by Z. 4 subtract 3i over -2 subtract 5i. This requires us to rationalize the denominator. So we're going to multiply by -2 plus 5i and -2 plus 5i. In fact, we're going to multiply by the fraction value of 1, which involves the conjugates, which we'll see in a moment. So in multiplying the top, we're going to use that binomial expansion. We're going to end up with -8 plus 20i take 6i, plus 6i, take 15i squared, and at the bottom we'll end up with 4. We've got take 10i plus 10i and take 25i squared. So in simplifying this, we can use our knowledge of I squared. So we're going to end up with -8 plus 15, that will leave us with 7, plus 26i at the top, and 4 plus 25, which will be 29. So this equates to 7 on 29 plus 26 on 29i. Our real part being 7/29, our imaginary 26/29. So we have something called the complex conjugate, and we've actually seen this used when we're rationalizing. The complex conjugate, or the conjugate, is simply the opposite value, or the negative value, I should say, of the imaginary part of our complex number. So if z is equal to a plus bi, then the conjugate is z with the bar at the top, and is equal to a subtract bi. So if we look at w and z, the conjugate of complex number w would be 4 plus 3i, and for our z would be -2 plus 5i. And that's what we've used when we've rationalised the denominator earlier. When we multiply a complex number by its conjugate, as you would have seen when we rationalised, what we find is we end up with I squared, because we've got a binomial expansion. But even more interestingly, we know our values cancel, but we end up with a real number when we multiply by a complex number and its conjugate. We've had a brief look at the Argand diagram of how we can plot a complex number on the Argand diagram in the complex plane. So in green, I'm just going to plot, for example, z, which was -2 subtract 5i. So that's going to take us down to here for z in green. Now we know the complex conjugate, as we found earlier for z, is -2 plus 5i. So if I plot that in orange, we're going to go -2 plus 5i, and we find that the complex number and its conjugate are a reflection in our real axis, or our horizontal axis. And if we plotted w, which was 4 subtract 3i, so we'll do this one in blue, and in pink we can have the reflection of that, or the conjugate of w, which will be 4 plus 3i, and we can see through that reflection line of the real axis. So now I'd like you to pause the video and have a go at the 4 questions that follow. Using your understanding now of how we can add and subtract with complex numbers and how we multiply and divide, making sure that when we're dividing or we end up with a square root as a denominator, we need to rationalise that denominator. And then you can come back and unpause the video and check your solutions. And checking your solutions. Just being careful in question 3, part B, that if it's -2 plus bi, so just writing your complex number in terms of real plus imaginary, so you can clearly see the conjugate that you're going to multiply by to rationalise that denominator. And in question 4, our 2 solutions, if x equals to solve for x, remembering that our general form, x take p, x take q, if you like, for a binomial product from a quadratic. Most of the time, I think most people would use x minus m, x minus n. So we're going to start with the x subtract, putting in our solution, and x subtract, putting in our solution.